In this lesson, we will discuss the electrochemical cell. The following procedure is used in the setting up of an electrochemical cell. Click to play the video and note how this electrochemical cell is set up.
The following procedure is used in the setting up of an electrochemical cell. Apparatus: two 250 cubic centimeter beakers, switch, small bulb 2.5 volts, fitted with a bulb holder, ammeter, voltmeter, connecting wires and crocodile clips. Chemicals: 1 molar copper 2 sulfate, 1 molar zinc 2 sulfate, 1 molar potassium nitrate, copper and zinc strips, strip of filter paper. Procedure: put about 200 cubic centimeters of 1 molar zinc 2 sulfate in a beaker and dip a clean zinc metal strip into it. Put about 200 cubic centimeters of 1 molar copper 2 sulfate solution into another beaker and dip a clean copper metal strip into it. Connect the solution in the beaker with a strip of filter paper that has been soaked in 1 molar potassium nitrate. Connect the two metal strips using the connecting wires. Connect the switch and the bulb holder to complete the circuit. Put on the switch to complete the circuit. In place of a bulb, connect a voltmeter.
When the switch is closed, the bulb lights, indicating that there is a flow of electrons through the wire. The ammeter and voltmeter are used to measure electric current and potential difference respectively. When the circuit is complete, the concentration of zinc ion, which was in beaker A half cell, increases as the zinc strip dissolves. Zinc gives up electrons in the process. This is an oxidation half reaction. These electrons then flow in the external circuit. The reaction would stop if the net increase in the positive charge is not removed. The reaction does not stop because the positive charges in beaker A are removed either by zinc ions moving into the salt bridge or nitrate ions moving out of the salt bridge into the beaker with zinc ions. The concentration of copper ions in beaker B decreases because the main electrons given up by zinc and are converted to solid copper, which is deposited on the copper strip. An excess of sulfate ions is left in the solution, which leads to excessive negative charge in beaker B. This excess negative charge is removed either by potassium ions moving out of the salt bridge into the beaker containing copper sulfate in aqueous, or sulfate ions moving into the salt bridge. The salt bridge has two main functions. It provides positive and negative ions to replace the ones consumed in the reduction half reaction and to balance the charges of ions from the oxidation half reaction. It completes the circuit by allowing ions to move from one half cell to the other. The following is the electrochemical cell.
When a strip of zinc metal is immersed in an aqueous copper-2 sulfate solution, electrons are transferred from zinc to the copper-2 ions. Copper metal deposits on the zinc strip and collects at the bottom of the flask. Zinc atoms are oxidized to zinc-2 ions, which enter the solution. This spontaneous oxidation-reduction reaction is summarized in the chemical equation shown. The spontaneous copper-zinc oxidation-reduction reaction can be made to yield useful electrical work by incorporating it in a voltaic cell. The zinc electrode is immersed in a solution of zinc sulfate. The copper electrode is immersed in a solution of copper-2 sulfate. No current flows through the light bulb because the electrical circuit is not complete. To complete the electrical circuit, we add a tubular bridge filled with aqueous sodium sulfate solution with a porous plug on each end. We now have a complete circuit and current flows. When we replace the light bulb with a voltmeter, we find that the cell has a potential or voltage of 1.1 volts. The copper electrode is the positive electrode, and the zinc electrode is the negative electrode. As the cell reaction proceeds, zinc atoms of the zinc electrode lose electrons and move into the solution as zinc ions. At the same time, copper-2 ions acquire electrons at the copper electrode and form copper metal. The reaction in the left-hand compartment is oxidation of zinc. The electrode at which oxidation occurs is called the anode. The reaction in the right-hand compartment is reduction of copper. The electrode at which reduction occurs is called the cathode. Electrons flow from the anode to the cathode through the external circuit. To maintain electrical neutrality in the two cell compartments, ions must move through the salt bridge. In summary, remember that in a voltaic cell, the anode at which oxidation occurs is the negative electrode. The cathode at which reduction occurs is the positive electrode. Electrons flow through.
The standard's electrode potential is the potential between an electrode and a solution of its ions of 25 degrees Celsius when all gaseous reactants and products are at a partial pressure, or 1 atmosphere, and all other soluble substances in the reaction are at a concentration of 1 mole per liter each. For uniformity, a hydrogen half cell is chosen. It is arbitrarily assigned an electrode potential of 0. All other single electrode potentials are referred to as potentials on the hydrogen scale. If the electrode reaction when connected to the standard hydrogen electrode involves reduction, for example consumption of electrons, the electrode is given a positive sign. If it involves oxidation, that is, liberation of electrons, the electrode potential is given a negative sign. Thus, the standard electrode potentials are sometimes referred to as standard reduction potentials. The table below shows standard electrode potential of some half cells. The electrochemical cell described above can be denoted as illustrated below. By convention, the half cell of the more reactive metal is placed on the left-hand side. Hydrogen electrode if part of the cell is placed on the left. A single line represents a change in state or a phase between the metals and their ions. For example, zinc and zinc ions. Double line or double dotted indicates the salt bridge. By conversion, the more electropositive electrode, one that does not ionize easily, is put on the right-hand side. The EMF of the cell is given by E cell equals to E right-hand side electrode minus E left-hand side electrode, or simply E cell equals to E RHS minus E LHS. The voltage of the cell is also known as the electromotive force EMF. The following is a worked-out example showing how to calculate the EMF of an electrochemical cell between zinc and copper. The following is a worked-out example showing how to calculate the EMF of an electrochemical between iron and copper.